Good day, attendees and fellow contributors. Thank you for giving me the opportunity to present at Campus ACM 2023, and thank you for joining me. Today, I will be presenting a simulated study exploring and testing Fuzzy Logic AI and IoT-enabled hydroponic dosing systems aimed at rural subsistence farmers in South Africa. So why is the study aimed at subsistence farming in South Africa? Soil degradation, land appropriation, and urbanization are contributing to environmental breakdown. Conventional methods of crop farming in South Africa are reliant on soil and irrigation in regions with rainfall that is becoming unreliable. That, combined with rising energy and water prices, is increasing farming costs. This is causing declining food securities due to the rising food costs and the inflation rates. So why hydroponics? Well, hydroponics is a water-efficient farming technique, and it eliminates the need for soil. It allows farming in various locations, rooftops, indoors, terraces, etc., places that were previously inaccessible to grow plants. Nutrient film technique, NFT, is the most prominent hydroponic method. It enables vertical farming and the reuse of water. It also grants more control over crop condition and maximizes space efficiency. For these reasons, hydroponics can help overcome challenges faced by subsistence farmers in South Africa, such as water scarcity and limited land. It has the potential to increase crop yields and reduce the labor intensity. However, there's still a human effort involved, which is to monitor and maintain the optimal levels of the system, such as the pH levels, the humidity, the temperature values, etc. And there can also be high initial costs associated with hydroponics, including the hardware and the setup. For this reason, we introduce IoT and AI to hydroponics. And smart farming is the utilizing of IoT devices to monitor and automate farming processes. IoT sensors and AI algorithms can optimize nutrient delivery and adjust environmental factors for maximum crop growth so that the farmers don't have to. Fuzzy Logic is an AI technique which handles uncertainties in different systems. Fuzzy Logic can regulate outputs based on intermediate degrees of truth, suitable for systems with varying parameters. So this paper actually forms part of an ongoing study to explore the use of AI and IoT-enabled hydroponic systems with rural subsistence farmers in South Africa. So this paper reports on phase 1, which is the testing and evaluation of Fuzzy Logic as an appropriate AI algorithm to assist in the optimization and automation of an NFT hydroponic system. This will add to the understanding of how to mitigate food insecurities in South Africa. So the proposed hydroponic system is actually a 72-hole NFT grow stand that's made of food-grade PVC with multiple tiers. So to create a controlled environment for the hydroponic system, we'll use a nylon grow tent. And the system that you see here will be, which is the PVC hydroponic stand, will be placed within the grow tent. We will be making adjustments to light levels, temperature, humidity, as well as the pH and the EC, which is electronic conductivity of the solution. This will be done to optimize crop growth and limit the impact of pests. So the IoT network that is proposed to be implemented to monitor the hydroponic system will, initially for this paper, we have a simulated network of sensors. But the data is collected by a microcontroller, which is an ESP8266 WeMOS board, and it's transmitted to a cloud-based data processing platform called ThingSpeak, which we can see later. It is then fed to the Fuzzy Logic AI model, which takes in input parameters such as pH, EC, which is electronic conductivity, the air temperature, and the humidity. It processes this data to determine what action the hydroponic system needs to take, and then the hydroponics, and in this way it's able to control the pH, so to add acid or alkali. It can control the EC by adding salts or water, and it can control other environmental factors such as adjusting the lights or adjusting the extractor fans, and this will help control humidity and temperature inside of the grow tent. So the model was evaluated using real world data from an existing automated hydroponic system, and it was also evaluated using simulated data or randomized data from an Arduino based microcontroller. This was to ensure that the Fuzzy Logic AI model provides accurate outputs for given inputs, supporting its real-time capabilities in the IoT network. So it's planned to deploy hydroponic systems with rural subsistence farmers in both Sweetwaters and KwaZulu. These rural areas in South Africa will benefit from this technology, and hopefully it will be able to enhance sustainable food growth and reduce the amount of human effort. So while the model derived from this research will be freely available, as mentioned earlier, the initial technology required can be quite costly, and which is limiting immediate accessibility. Additionally, technical aspects of the IoT implementation may pose challenging for subsistence farmers which are unfamiliar with such technologies. So let's look at some of the findings when evaluating the model. In the initial evaluation, when passing a single set of randomly generated inputs, the inputs being temperature, humidity, pH, and EC, we simulated the model and we plotted the degree of membership for each consequent. And we saw that the model provided accurate, crisp outputs and associated linguistic values for each consequent. So, like when given low air temperature and low humidity, the lights were correctly told to set to high and the fans to off. Also, when given like a low pH, the pH control was set to add alkali to adjust this correctly. And with high electrical conductivity, the solution control was set to add water. These are just degrees of membership plots which show the consequent crisp and linguistic output values are derived from the antecedent crisp input values. So we then further evaluated the model's performance by giving it 100 sets of random inputs, so that we could cover the entire range of what these levels could be. So each set of input was simulated, and the resulting outputs were mapped on this 3D plot. And the plot confirms that the model accurately calculates crisp outputs across all ranges, whether using a 2-to-1 relationship or 1-to-1 relationship of antecedent to consequent. We then evaluated using a real-world test. We used data collected from an existing hydroponic system, and the data was cleaned, converted into appropriate units, and passed to the model. The outputs were analyzed and compared against linguistic values, and the findings were inconclusive because the diversity of the data over the time that data was collected was just not substantial enough. So to address this data diversity issue, we simulated data and passed it to the model. We used over 500 records, and the results became more diverse and conclusive. The model demonstrated accurate degrees of membership between antecedents and consequence, providing precise outputs for specific inputs. So the study found that the Fuzzy Logic AI model could accurately assign degrees of membership between inputs and outputs, and similar results were observed in other research, suggesting that the technology can be used for first-time growers and rural farmers who are new to hydroponics. So for farmers in regions with limited resources, an optimized Fuzzy Logic enabled system could reduce waste and energy consumption. During the study, we realized that cloud-based solutions might not be ideal because of high data costs in the region. Instead, we recommend that we implement a local Wi-Fi network for communication with the microcontroller. And additionally, it's crucial to allow farmers to interact with the AI and adjust settings, and we therefore propose incorporating a mobile application for this purpose. In future work, we plan to deploy the complete hydroponic system with improvements mentioned earlier. Solar power will also be added to the system, considering the ongoing energy crisis in South Africa, and along with a built rechargeable battery pack. So while Fuzzy Logic AI has shown promising results, a limitation lies in the need for human-provided expert levels for optimal environment values and rules. To address this, we propose using a machine learning, possibly a RNN, a recurrent neural network, to update membership functions and rules based on collected data from successful growth cycles. This integration could optimize the Fuzzy Logic model and provide valuable insights for future and expert models.